Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone and welcome back to part 6 on mass spectrometry. In the previous two lectures, we covered the fragmentation of functional groups alkanes, alkenes, alkynes, aromatics, alcohols, ether, aldehydes, and ketones. We will continue on today fragmentation of esters. The molecular ion peak is usually weak in esters. An important fragmentation pattern involves alpha cleavage, breaking either bond to the carbonyl carbon. Loss of alkoxy group is the most important of these fragmentation as shown. This is the alkoxy group. Assuming that we make ionization on the lone pair of oxygen, we kick out 1. Elimination of alkoxy radical will leave radical in here with this radical to form a triple bond O plus at 43. If we cleave this bond from that side, then again radical with that radical to form triple bond, oxygen has plus, and this will lead to ion at 73 m/e. Another fragmentation pathway from the molecular ion 88 is H transfer. Here we will attack the leaving this here radical, forming radical in here. Okay, O will be OH plus. Now the oxygen will go and get H radical. At the same time, this bond will be cleaved, eliminating minus C2H3 H, and here radical minus 27, giving us cation at 61. Here is 61, here is 73, here is 43, beside weak molecular ion. But what about 70? It's 88 to 70 minus 18. And minus 18 most likely to be minus water. How we can eliminate water out? All right. Once again, we will do the same. Here, radical, leaving this radical, okay. And this will be plus, all right. Now, breaking this homolytic with this odd electron will be here. Odd electron with odd electron, and oxygen will have odd. Okay, so we'll end up with this cation radical. Right? Then one more time, this odd electron with hydrogen, this will be OH2, and here will be radical. Then minus water out, leaving here plus. Right? This I can write it this way, double bond, cation radical. This at m/e 70. We eliminated water. Also in ester, we can see McLafferty rearrangement. If you have an ester, okay, with more than 1, 2, 3, 4 carbon, so it has alpha, beta, gamma. This hydrogen can transfer by attacking double bond on this hydrogen. These two electrons will make a bond, and this bond will be cleaved, okay, and form a double bond in here. So we'll have double bond, O, BOH, cation radical, and you have here O. This will give you ion at 74, space peak. So McLafferty fragmentation or rearrangement causes a highly stable ion at 74. Having a metal hexanoate as an example, a molecular ion at 130, very weak, or we can see it even, okay, and then elimination of methyl group give C5H3O2 plus. That's for McLafferty, and this one is from the elimination of all the alkyl part, okay, and the 71 will be this alkyl part, okay. So 55 is this part, and 71 is that one. All right. Fragmentation of carboxylic acids. The molecular ion peak is weak, but usually observable. An important fragmentation pattern involves, again, alpha cleavage. So either you cleave this bond or that bond. So if we get out OH radical, we will form ion at 85. If we cleave this part as a radical, CO2H radical, will give you a peak at 57. But again, this alkyl group, we can eliminate part of it. So if you eliminate methyl, you get peak at 87. If you cleave the SL group, you will end up with 73. Loss of the alkyl group as a free radical, leaving CO2H cation, also occurs. If you have alpha radical in here, eliminating of alkyl radical will leave C double bond O, OH cation at 45. With acids having a gamma hydrogen, the principal pathway for rearrangement is the McLafferty rearrangement. Here we can have heterolytic cleavage, abstracting H, forming double bond, breaking this single bond, and forming the double bond, leading to a cation radical at M over E60. Remember, you started with odd. You eliminate neutral species. You have to end up with odd cation radical. Okay? An example of typical butanoic acid. You have here very weak molecular ion. You have the peak at 87 and 73 and 60. So all the intense peak can be entered, no problem. Fragmentation of amines. The molecular ion peak is weak or absent. When observable, will be a good indication of the presence of amine nitrogen rule. You remember that we mentioned that if you have an odd number of nitrogen, you get an odd molecular ion peak. An important fragmentation pattern involves cleavage of the bond to alpha carbon. So if this is alpha and this is alpha, if we break this bond, eliminating CH3 radical, here we will have odd electron. If we started with ionization of the lone pair, so we have here odd electron 2, this will lead to the formation of bond, so it will be a double bond. Of course, this species, okay, is stable via resonance, and here is right, having these two electrons to the nitrogen, okay, and this is showing up at 58. Loss of hydrogen radical is quite common in amines. So if we started with molecular ion having NH and we ionize the nitrogen, kicking out H radical will lead to the formation of ion at 72. In the spectrum, we can see clearly a peak at 30. How we can get to this peak? Assuming that the molecular ion has hydrogen transfer with elimination of CH2, double bond CH2, neutral species, you end up with N cation radical. Nitrogen has 2 hydrogen. Okay, now we eliminate CH3 radical, we end up with the ion at 30. Okay, this ion is stable again via resonance. Here is a molecular ion at 73, elimination of 1H showing very well, no problem. Elimination of CH3 at 58, elimination of ethyl show a peak at 44, and a peak at 30, which we explained its formation in the previous slide. Fragmentation of amides. The molecular ion peak is usually observable and will be a good indication of the presence of amide, again nitrogen rule. An important fragmentation pattern involves alpha cleavage, breaking either bond to the carbonyl carbon. So either we eliminate NH2 radical to form peak at 85, or eliminate the alkyl part, okay, to eliminate C4H9 radical, leaving ion at 44. Remember, we have an odd, we eliminate radical, we should get even, just only plus. McLafferty rearrangement can take place for amide 2 if you have again more than 4 carbon So we have here alpha, beta, gamma. This hydrogen is close to the oxygen, abstracting H, forming double bond, breaking single bond, get neutral species out, leaving peak at 59. Now we get to the nitrile. The molecular ion peak is usually too weak to be observed. However, the loss of hydrogen radical will almost always produce an observable peak. For nitrile, then M-1 peak is usually more prominent than M plus radical peak. McLafferty rearrangement can take place in nitrile. Once again, attack, forming double bond, breaking the bond, getting the neutral part out, forming cation radical. You start with odd, you eliminate neutral, you get an odd. Elimination of hydrogen radical, you will end up with this ion at 82. If you eliminate methyl, you get peak at 68. If you eliminate ethyl, you get peak at 54. If you eliminate this species, forming carbon, 2, 3 carbons, will give you peak at 43. This is 43, 41, 54, and molecular ion. You can see that's very small, and you can see M-1. All right. Fragmentation of alkyl halide. The molecular ion peak has characteristic isotope peaks, depends on the nature of halide. Most elements have one major isotope, notable exception. Chlorine 35 and chlorine 37 occurs in ratio 3 to 1. Thus, there are two peaks in a ratio 3 to 1 for the molecular ion, because it will contain the halogen of the alkyl halide. Bromine has two isotopes, Br79 and Br81, in ratio 1 to 1. Thus, when the molecular ion consists of two peaks, M and M plus 2, in a ratio 1 to 1, a 1 bromine atom is present. However, iodine may be lost as I plus, so you will see a peak at M over E at 127. A gap of 127 in the spectrum as well as a peak at 127 is good indication for alkyl iodide. An important fragmentation pattern involves first elimination of HCl. This is a neutral. You will end up with ion cation radical because HCl is neutral. If you eliminate C2H5, then you will end up with halonium ion. Since this species contain Cl, this means that you are going to see M over E and M over E plus 2 for the species. So you will see 105, 107 in 3 to 1 ratio, indicate the presence of Cl in this species. Okay. We can also see kind of Maklafer-T rearrangement. Cl will attack H abstraction, forming double bond, breaking the single bond. Then you will end up with peak at 56 cation radical. Okay, so here you eliminate HCl, you eliminate CH3, C, double bond, so you'll make two species, leaving the cation radical. Here is neutral, here is neutral. You start out with odd, you have to end up with odd. This is a molecular ion. This is a cyclic halonium. This is elimination of HCl. This is a peak at 69, and this is the one at 56. To make a summary out of it, if we see peak at 15, the most likely the fragment is CH3+. M over E at 18 means H2O+. 26, this means we have CH2, CH2+. 28 depends on the compounds. If carbonyl compounds, CO+, C2H4+, CH2N+, N2+. It depends on your compound. If it's nitrogen containing compound, you may expect these last two. 29, it's 2C2H5+. If it's 30, then you have CH2NH2, and this is an indication that you have a primary amine. If CH2OH, then you have a primary alcohol. If you have HCl, the alkyl halide, CH3CO+, C3H7+, that's causing peak at 43. 44 could be OCO, or it's OCNH2 plus if you have a primary amide, or CO2 plus if you have an ester carboxylic acid, CH2CHOH if you have an aldehyde, and so on. We look for characteristic fragmentations formed by loss of common ions and neutral fragments. If you have the M plus radical minus 1, then you eliminate H radical, which means that most likely you have an aldehyde or tertiary alcohol or amines. If you lose 2, you have secondary alcohol. If you lose 3, it's multiple elimination of hydrogen, you lose primary alcohols. If you eliminate CH3, you have variable methyl group, methyl ester. If you have M-16, you eliminate O radical peroxides. If you have M-17, then you lose OH radical, means that you have alcohol or phenols or carboxylic acids. If you have M minus water, then you have eliminate water out and you have alcohols. If you eliminate 19, means that you have fluorocompounds. If you can see in the fragmentation M minus 20, this means elimination of HF, you have fluorocompounds, and etc. All right. We have studied the fragmentation of functional group. However, in the new century, 21st century, is a little bit different. You have a lot of softwares that you can only feed the software with the structure in certain format, and the program will predict all the fragmentation that could take place in this structure. And this site contains several software. It's free on the net. You may try. We will try together and see. Here is software where I can just draw the chemical structure and will convert the chemical structure to what they call it SMILES code, which I needed in the next program. Here is a program where you can spectra prediction, which can use it for the prediction of the fragmentation. Here you put the SMILES form of your compound. This drop box you can use to select either you have electron spray ionization or electron impact. Of course, I use the electron impact. I left here in the positive mode. Then this one, this drop, I choose unknown. Okay. And then I push the bottom submit. Here is the molecular ion for cyclohexene at 82, and the fragment structure. The fragments at 66, at 67, 56, 54, 52, etc., going down lower molecular mass. Thanks for watching, and see you in the next lecture. IR and mass spec solving problem strategies. Bye bye.